Welcome back to Differential Calculus. I'm your tutor Ryan, and today's lesson is part 5 of basic derivatives. And we'll be moving on to exponential functions for this video or series of videos. So let's get started. Here are today's 7 problems for the exponential section, and we'll also be covering the chain rule and quotient rule in the later sections of the questions, parts 6 and 7. Okay. First, we need to ask a question about exponentials in order to learn things in order for us to move on. So let's get started on that. The first type of question we're going to ask is, what type of equation is an exponential one? Well, they possess the form y equals c multiplied by a to the exponent x. The letter c can be just about any function, variable, or number. The letter a is any positive real number, and the exponent x is the variable which changes and does not have any set value. Now keep in mind that x can become anything. It can become 5x, it can become a logarithmic equation, it can become another exponential, it can be just about anything. So that's where it gets a little difficult, and we'll see that in the later problems. The second question we're going to ask is, what interesting characteristics do exponential functions possess? Well, the slope of an exponential function is equal to the value of the function at that given point. That is to say that an exponential function grows at a rate which is proportional to its current value. So, if y is equal to a to the exponent x, then the slope of that function at that point is also equal to a to the exponent x. Also, there exists a special number e for the exponential functions, which has a never-ending number of decimal points, and its value is approximately 2.7183. The derivative of y equals a to the exponent x is y prime equals a to the exponent x multiplied by ln of whatever the value of a happens to be multiplied by the derivative of whatever happens to be the exponent. Keep that in mind. It'll become very important for later on, so you might want to write that down. Also, y equal to ln of x simply means log base e of x. Alright, let's move on. Alright, the last question we may wish to ask about exponentials is, in general, what do exponential functions look like? Well, here I have 4. We have y equals 1 to the power x, which is always just 1 no matter what the power is. We have y equals 2 to the power x, y equals 3 to the power x, and y equals 4 to the power x. You can see that as the base, which is a, changes, the slope of the function increases gradually, but it reaches a limit eventually. Alright, let's move on to some interesting facts about exponentials. Interesting fact about an exponential. Its derivative is equal to itself. That's as long as y is equal to e to the exponent x. And the reason this works is, using the derivative of y prime equal to e to the exponent x ln e multiplied by the derivative of whatever x is, gives you y prime equals e to the x times ln of e, which is equal to 1, times x prime, which is equal to 1, as long as x itself is just x, because the derivative of x, as we learned from the polynomial section, is just 1. Alrighty, let's move on to the problems. Problem 1. Find the derivative of y equals a to the exponent x. This is just sort of a re-warm-up for us because we've already learned previously what the derivative of y equals a to the exponent x is, and that happens to be a to the exponent x multiplied by ln of whatever a happens to be multiplied by the derivative of whatever x happens to be. Alright, it's pretty simple. Keep that in mind, write it down, whatever works for you. Next problem. Problem 2. Find the derivative of y equals a to the exponent x squared. Things aren't getting much more difficult at this point, as long as you followed through the polynomials section. So using the derivative of y prime equals a to the exponent x times ln a multiplied by x prime, we can find that the derivative is equal to y prime equal to a to the exponent of x squared ln of a multiplied by the derivative of the exponent, and the exponent's derivative happens to be 2x. So the answer is y prime equal to 2x multiplied by a to the exponent x squared multiplied by ln of a. Simple enough. Problem 3. Find the derivative of y equals 2 to the exponent x. Well, from the already known derivative of an exponential, we can find that y prime is equal to 2 to the exponent x multiplied by ln of 2. And ln of 2 is approximately equal to 0.693. So if you wanted to, you could say that the answer is 0.693 to the multiplied by 2 to the exponent x. Alright, let's move on to problem 4. Find the derivative of y equals e to the exponent x. This looks familiar. Still, we use the already known derivative of an exponential, and we get y prime is equal to e to the exponent x multiplied by ln of e. And ln of e simply equals 1, so we just get y prime equals e to the exponent x. We already knew that. Nothing surprising there. Let's move on to some stuff that's a little bit more difficult, shall we? Problem number 5. Find the derivative of y equals sine of e to the exponent 2x. Now, I'd love to just jump into this problem, but first we need to learn the chain rule. You all seen it coming, and here it is. The chain rule states, if g of x is differentiable at x and f of x is differentiable at g, then there is a composite function, f of x, which equals f composite g, written as capital F of x equal to f of g of x. And this is differentiable at the point x, and the derivative f prime of x is found via the following product. F prime of x equals f prime g of x multiplied by the derivative of whatever function g of x happens to be. So now let's go through this slowly and we'll see it in actual use. Alright, we have isolated here on the screen what we know about the chain rule. So what we're going to do is we're going to break this up so it's easier to understand for the composites. We have f as a function of u, and that's equal to sine of u. And we have u of x equal to e to the exponent 2x. So when we put the u of x inside the u location of sine, we're going to get sine of e to the 2x. And that's what it looks like, so that'll help us use the chain rule in order to solve this problem. So we'll put that over to the side, and we'll start solving the problem using what we already know. Wait, but first I need to tell you that, as you can see in the sidebar, we have f of u equals sine of u. And the derivative of sine of u is equal to cos of u multiplied by the derivative of whatever u happens to be. It could be a function of any sort. So keep that in mind. You'll learn that later on in the derivatives of trigonometrics section. But for now, that's good, so we'll move on. Keep it in mind. Alright, so stated there, we have the method of finding a derivative via using the chain rule. Beneath it, we have f prime g of x and g prime of x. We need those in order to continue. So f prime g of x is equal to cos of e to the exponent 2x, and that's because the derivative of sine is cos, and we keep what's in the brackets. Now we need to find the derivative of what's in the brackets, and that happens to be the derivative of an exponential e to the exponent 2x. And from the equation we learned previously in this video, we take the derivative of the exponent, multiply it to the function, and multiply it by ln of whatever the base happens to be. So we get 2e to the exponent 2x. So putting that all together into one giant answer, we get y prime is equal to cos of e to the exponent 2x multiplied by 2e to the exponent 2x. Alrighty, that is all for this video. Part 6 will cover questions number 6 and 7, and we'll be covering the quotient rule, another method of finding derivatives, and that'll be for problem 7. So stay tuned, don't forget to rate, favorite, comment, do all those things, because it always helps out. Thank you.